Homework Solution 3.12. A three-phase line with an impedance of 0.2 plus j 1.0 ohms per phase feeds three balanced three-phase loads connected in parallel. Load 1 absorbs a total of 150 kilowatts and 120 kilovar. Load 2 is delta connected with an impedance of 150 minus j 48 ohms per phase. Load 3 is 120 kVA at 0.6 power factor leading. If the line to neutral voltage at the load end of the line is 2000 volts, determine the magnitude of the line-to-line voltage at the source end of the line. The givens in this problem statement I think are best described just using a circuit diagram. We've got the input end of some sort of three-phase transmission line. I'm going to draw it on a per-phase basis. So we know that we typically will use the A phase to do that. So there's the input end of the transmission line, AN. Voltage at that end is going to be VAN. This T line has per phase a series impedance that looks inductive, and that was specified to us as 0.2 plus J1. And then what we've got is three parallel loads. Z1, Z2, and Z3. And we know that the load voltage was specified to be 2000 volts. By convention, that's capital A, and that's capital N right there. So we were given that information. We're also told a little bit about each of these loads. I wrote line there, but Z loads. Load 1, we were told that it absorbs 150 kilowatts and 120 kilovar, so that means the power is equal to, on a three-phase basis, is equal to 150 kW. And we know that the Q on a three-phase basis is equal to positive 120 kilovar. It says it absorbs, so that means positive 120 kilovar. For load 2, we were just told that it's a delta connected at 150 minus j 48 ohms per phase. And then for load 3, we were told that S three-phase is equal to 120 kVA. And we were told that the power factor is equal to 0.6 and that the circuit was leading. So that's all our information. Find VAB, or the magnitude of VAB, the magnitude of the line-to-line voltage at the source end. It's not shown in a single phase equivalent, right? So the general solution method is we know what the load voltage from A to N is. To determine the source voltage from lowercase a/n, we just need to add whatever the voltage drop across this transmission line is. So in theory, pretty simple. This voltage plus this voltage is equal to this voltage right here. So no problem there. To determine the voltage drop here, what we need to know is the line current flowing through the feeder, and how we determine that is individual currents. We can determine how much current is drawn in each of these individual phases. I could either do that by analyzing each phase individually, or I can combine them together and determine what their total current draw is. I think it's a little quicker to do it that way, so that's the approach I'm going to take. To combine these three loads into one effective load, I have, again, two options. I can either analyze them on a power basis and then add them all together, or I can analyze them on an impedance basis and then you combine them using the rules for impedances in parallel. 1 over Z totals 1 over Z1 plus 1 over Z2 plus 1 over Z3. So your choice on how you'd like to approach that. Since two of the loads were already given to me in power form, I have to do less work if I just add S1, S total equals S1 plus S2 plus S3. So that's the approach I'm going to take in this problem, is to add the powers of the three loads together. Remember, powers in parallel just add. So the solution method that I'm going to use is that I need to decompose the loads into their single phase apparent powers, and so then I could just add them. For load 1, I was given a power triangle that looks like this on a three-phase basis. It's 150 kilovolt or kilowatts and 120 kilovar. So I need to determine what S is on a single-phase basis. I would draw the power triangle for this, and I would just say magnitude of S is 150 squared plus 120 squared raised to the 1/2, and then phi is the inverse tangent of 120 over 150. That's kind of old hat for you guys at this point, so I know S of load 1 on a 3-phase basis is equal to 192,094 at an angle of 38.66 degrees volt amps. S1 on a phase basis is just 1/3 of that, and that's 64,031.2 at an angle of 38.66 degrees volt amps. So now I've tackled load 1. Load 2, I was told that the load impedance ZL for the delta load is 150 minus J48. So I've got to convert that over to S2 on a phase basis. So there's two ways to do that. I can either analyze this as a delta circuit using the line voltage and the delta impedance, or I can analyze this as a Y circuit using the phase voltage and a Y equivalent impedance. So since I drew a single phase equivalent model up here, I'm going to go ahead and convert this over to a delta equivalent or a Y equivalent model. To do that, that is Z Y equivalent is equal to Z delta over 3. So that's 150 minus J48 divided by 3. There we go, that looks a little better. And so that's going to give me 50 minus J16 ohms. So that Y equivalent sees that line to neutral voltage of 2000, so the one phase apparent power for load 2 is going to be the 2000 volts squared over Z star. So that's 2000 squared over 50 minus J16. So that's going to give me an answer of 76,193.9 at an angle of negative 17.74 degrees volt amps. If I had wanted to go the other direction, I could have found S2, one phase is going to be equal to root 3 times 2000. That converts that voltage, that phase voltage over to a line voltage. And then I would have divided that by 150 plus J48, the complex conjugate of the delta impedance. It'll give me the same number there. So you can go either way. We're just trying to get a power out of it. Just have to use the right voltage with the right impedance is really it. So that tackles the second load. Load 3, we were told, we were kind of given a power triangle here. We were told that the hypotenuse or the apparent power is 120 kVA. And we were told that the power factor is equal to 0.6, so that means phi is going to be found by taking the inverse cosine of 0.6, and that is inverse cosine of 0.6 is 53.13 degrees, which means S3 on a three-phase basis is going to be 120 at an angle of negative 53.13 degrees, because this was a leading circuit, and that's kVA. Again, S for load 3 on a single phase basis is just 1/3 of that, so 120 divided by 3 is 40 at an angle of negative 53.13 degrees kVA. As we said earlier, total load power is just the sum of the three. They're already on a per phase basis, so S total phase is equal to S total, S1 phase plus S2 phase plus S3 on a phase basis. So if you add all those up, you're going to get 147,357 volt amps at an angle of negative 5.93 degrees. I can now determine that line current that I was looking for by taking S total phase divided by VAN and take the complex conjugate of that. That's going to be 147,357 at an angle of plus 5.93 degrees divided by 2000. Angle 0. That gives me a line current 73.68 at an angle of 5.93 degrees amps. So if I want to know what VAN is, from my previous formula, it's going to be VAN plus IAA times Z line, which is 2000 angle 0 degrees plus 73.68 at an angle of 5.93 times, what was the line impedance? I've lost that. 0.2 plus J1. And solving that gives you a phase impedance for phase A of 2008 volts, 0.44, at an angle of 2.13 degrees. The line voltage for phase A is therefore root 3 angle 30 times VAN. It's going to give me 3,478.72 at an angle of 32.13 degrees. And so therefore the magnitude of the line voltage is 3,478.72 volts.